So first of all, thanks to the organizer for this very nice meeting, and also for the invitation. Actually, it's a great pleasure to be here, even if it was a short notice. Really nice. And thanks to the previous speakers, particularly to Eduardo, for setting up the stage of this topic. So title of my talk already tells you that I'm going to speak about non-equilibrium dynamics related of tantalum nickel selenide and related to an excitonic insulator material, possibly. Nevertheless, let me first start with thanks to the people involved in the project. So the measurements I'm showing you were performed in the group of Julia Steller, the Festhaber Institute in Berlin, where I recently finished my PhD, and were done in close collaboration with Claude Monet and Mark Herzog. And the theoretical calculation I'm showing you today were performed by Dennis here in the audience, which at that time was joining the group of Philipp Werner, and that was done in collaboration also with Martin Eckstein. And then other thanks go to Takashi Mizokawa, which helped us to understand our photoemission study, the group of Annette Tunschke, the Festhaber Institute, for providing us the Raman spectroscopy equipment, and eventually the sample growers for providing us the samples indeed. So we already learned a lot about excitonic insulator phase, so let me just give you like a pre-lunch recap of what is, in my opinion, relevant features of this phase, and this will also be important for our discussion. So an insulating phase, or like an excitonic insulator phase, seems to be like an insulating phase where an exciton population can populate already the ground state of the material. And two ingredients seems to be important to realize such a phase. So first of all, a weak screening of the Coulomb interaction, which allows for formation of excitons having binding energy larger than the electronic band gap. And a second, sufficiently low temperature for allow this spontaneously formed excitons to gain phase coherence and eventually condensate. And if these two requirements are satisfied, we might expect an excitonic insulator phase to realize upon opening of the electronic band gap by an amount twice delta, which can be taken as order parameter, and if we stay in a mean field picture, is sort of related to the density of these condensed excitons and their coupling strength, or the binding energy of the electron-hole pair. And both prediction and also experiments have shown that such electronic phase transition is combined with some lattice distortion. And there's a bit debate what is the role of the two, like electronic and lattice degrees of freedom, in the realization and stabilization of such phase. Now, in our work, we investigated the non-equilibrium, or we tried to investigate the non-equilibrium physics of an excitonic insulator. So let me first recall you what we might expect to happen upon photoexcitation of such a material. Now, in a semiconductor, it's observed in many materials that upon photoexcitation, a large fraction of free carriers is injected in the system, and this can transiently enhance the screening of the Coulomb interaction and leads to a transition of a material with more metallic-like character, and particularly a narrowing or renormalization of the electronic band gap is often observed. And this is just a very short list of materials where this has been observed indeed. Now, upon photoexcitation of an excitonic insulator, now we might expect some sort of screening enhanced dynamics going on, because of course, like free carriers are injected in the system upon photon absorption, but photon absorption will also create further excitons in the system, and the question arises whether these excitons might sort of contribute to the order parameter or the density of the condensate and somehow affect the electronic band gap in the opposite way. So our question was like, what is the ultra-fast dynamics of an excitonic insulator? And I will show you how tantalum nickel selenide, in our opinion, allowed us to address this question. So we already know the system is a layer crystal with atomic chains running along the A-axis, and this quasi-one-dimensional structure is also reflected in a rather simple electronic structure where the upper valence band is mainly formed by the orbitals of the nickel atoms, and the conduction band has mainly the character from the atom of tantalum. So which means that when we form excitons, they will be located mostly across the atomic chains. And now already the question arises how the distance, the interchange distance, might be sort of connected to the excitonic coupling. And there are already some evidences at the equilibrium that there is a connection So we know that we have this electronic and structural phase transition at a critical temperature of 330 Kelvin. And concerning the electronic part, the band gap opening is combined with a flattening of the valence band top, which models try to sort of reproduce. And this is actually results from the model, that is green line, by introducing in the Hamiltonian a Coulomb attraction term between the valence band and the conduction band. So already suggesting that this latent hole Coulomb attraction plays a role in flattening the upper valence band. Or this is at least was the interpretation. And at the same critical temperature, we have this structural distortion, which interestingly is sort of this involves the shearing motion of the two chains. And this shortens the distance between two nearest nickel and tantalum atoms. And it was also proposed that such shortening might sort of help the excitation of the two bands, and in this way might favor the excitonic coupling at low temperature. Now, in our work, I told you, we want to tackle the problem sort of in the time domain. And the question of my talks will be, how do the carrier and the lattice subsystems connect on an ultra-fast time scale? So how did their respective photo-induced dynamics are coupled? And how does the Coulomb interaction govern the non-equilibrium electronic structure? Whether we can learn something from this in regard to the excitonic condensate, which might be hosted by the material. Work tools are time-resolved photoemission and optical spectroscopy. In all experiments I will show you, we always pump the system in the low temperature phase. And so our pump photon energy is 1.55 electron volt, much larger than the electronic band gap. So those are the two transitions which are mainly involved in the photoexcitation. At the gamma point, from the upper valence bands into some high-lying conduction bands. And then at much larger K vector, we connect directly the upper valence band and the lowest conduction band. And then we tune our probe photon energy to be able to map both the occupied but also the unoccupied electronic bands. And by that, we follow the dynamics as a function of delay from following the photoexcitation. In the second study, so we wanted to be simultaneously sensitive to the carrier and lattice dynamics, and we did with transient relativity measurements. And in this case, different from previous work shown today, we probe the reflectivity at the wavelengths resonant to the electronic band gap, so at 4 microns, and while still exciting the system at much larger excitation energies. So, yep, sure.
How do you probe the unoccupied states? Is it because you heat initially the electrons and you have sensitivity?
So, this is by means of two-photon photoemission process.
Oh, you do 2 photons?
Yeah, exactly. So we still excite with 1.5 and then probe from the conduction band. I will show you that, yeah. So first results of our photoemission work is the effect of the photoexcitation mechanism at the gamma point. So what we see here is the valence band, actually the upper and also a lower valence band with maxima at gamma. And so if we follow the effect of the photoexcitation at the valence band top, what we found is, first of all, this blue is like a negative intensity in the differential spectra, so we are strongly depopulating the valence band top, and this whole population build-up is occurring rather abruptly, and then it decays on a few picosecond time scales. Now we follow this whole population build-up, and we found that this is dependent on the excitation density, but at a critical fluence FC of approximately 0.2 millijoule per square centimeters, the whole population buildup saturates at 50%. And no matter how higher you pump, you don't create further holes in the valence band top. So we interpreted this as an effect of pump absorption saturation of this transition mechanism A at the gamma point above FC. So meaning that above this, there's no further electrons can be excited from the valence band top. So let's see how this actually connects to the photon-induced dynamics in the carrier and the lattice. And for that, we switch to our optical probe, where we find that the mid-infrared incoherent optical response follows very well the whole population, the temporal evolution of the whole population excited at the gamma point, which already connects our optical probe to the whole dynamics excited at gamma. And this is also consistent with the fluence dependent of the incoherent response amplitude, which exhibit a strong suppression at a comparable critical excitation density Fc. Nevertheless, at higher excitation density, we still see a slight increase in the incoherent response amplitude. So our conclusion is the following. So while at the gamma point, so we have a saturating mechanism, which is also sort of the mostly coupled to the optical response. The other excitation mechanism at large momenta does not saturate and sort of like takes care of this light increase at higher excitation density. And this is actually quite important for what I will discuss later in regard to the dynamics of the electronic band structure.
Just to be on the same ground.
Yeah.
Whatever you have told us up to now applies to an excitonic insulator as well as to a normal semiconductor.
Yeah, free carriers dynamics.
We learned anything new.
So far, nothing. Also, I mean, apart that, keep saying, so what we are sensitive here, so up to now, this dynamics I'm showing you is somehow like connected to the dynamics at the gamma point, but it's so far free carriers dynamics.
Exactly. And then you get all this bleaching, which is the normal thing at gamma now. Okay.
Yeah, perfect. So what about the lattice dynamics? We now therefore like look at the coherent response of the optical response, and so by Fourier transforming the coherent part above and below the critical temperature, so we see that the phonon spectra changes quite much, and there are two modes at 2 and 4 terahertz which disappear above in the high temperature phase. So we can follow their dynamics sort of to see how their photon-induced dynamics evolve in the low temperature phase.
So
and particularly,
there are two new modes of light.
Yeah, well, seems like. So we have like, yeah, so we also compare this with Raman Spectra, and so we would have like a mode at 2 terahertz, which also Stefan reported, 3 terahertz, and then 3.7 and 4. And the 2 and the 4 are the one that in our result are like strongly temperature dependent because they disappear above Tc. While the 3 and the 3.7 stay always still there.
I see. I see. So those two red modes, they've just got bigger, but they're really the same as you were seeing.
Exactly. Yeah, I normalized to the maximum sort of, but
normalization.
Yeah, just normalized.
What's happening with the 1 terahertz?
So there is a difference in the pumping polarization. So we are pumping parallel to the chain, and actually the 1 terahertz is not present in our
Okay.
But we're also probing with a different wavelength. So I mean, matrix element in the Raman process is also.
That's also something we did is also in plane. We see the 1 terahertz mode also in plane, but if you just pump quite strong, it's very easy to suppress the mode in plane. And then this really depends on the fluence. If you take a little bit too high fluence, it's very easy to suppress this mode. Because it's very easy to excite in our picture the condensator, deplete the condensator, and then this mode.
But it is clear that these are separate modes and not overtones of a 1 terahertz.
Yeah. Okay. Another interesting thing, so I can tell you which mode this 4 terahertz, which is maybe the newest now, so which mode is this, but it's strongly like polarization dependent, and we can see that if as soon as you go with polarization, even in the Raman, not even like this Korean from Raman spectroscopy, if you go perpendicular to the atomic chains, the 4 terahertz is not that pronounced, and it becomes the dominant feature in the Raman when you go parallel, and meaning that actually there is like a component like in the dipole which like sort of like is mostly oscillating along the chain, and this is like at 4 terahertz. Nevertheless, our point in the study is the following. So if we look at the initial amplitude of these 2 low temperature phonon modes, we find that they are like fluence dependent and they completely saturate above this critical fluence Fc. So which means already that the coherent excitation of the lattice are caused by a coupling with mainly this transition at the gamma point, which is the one that saturates. Second thing, this amplitude never go to 0, so we don't have any like instantaneous switch of the phase, which would turn in a 0 amplitude of those phonons. Looking at the decay, they both spans on like a few picoseconds. So one is has a decay which is fully fluence independent. The other one actually follows again the fluence dependence of like the amount of free carriers which we are exciting at the gamma point, as signalized again by this saturation. Nevertheless, again, is set to something like 1.5 picosecond. This time scale is also relatively long to sort of like assume a delayed but still non-thermal structural change. So what we concluded is somehow in the system we do not photoinduce the structural change, and all the saturation behaviors suggest that the blocking mechanism relies on the occurrence of pump absorption saturation at the gamma point, limiting the optical perturbation of the lattice. So just to sum up this first part.
There is no heating.
Well, on a very longer time scales, there might be some heating process, but then it would no longer be like a photoinduced, but rather a thermal effect. Yeah. So, quick summary of this first part. So I've shown you that like the coherent excitation of the lattice occurs via coupling of phonons to displacement of charges which are excited at the gamma point, as signalized by the saturating mechanism. And I forgot to put the USB. Anyway, and the second thing is that the occurrence of optical absorption saturation at gamma limits the amount of free carriers that are excited and that they can couple to the phonons and eventually like induce a structural change, which in this case remains inhibited.
And Selene, those
Yes.
phonons here at 2.1 and 4,
Yeah.
what modes are they?
We don't exactly know which modes are there. I just can tell you about this polarization dependence. So they have a strong component along the chains.
But there hasn't been a calculation that
There hasn't been a
helped you
calculation.
identify.
So no, unfortunately, we asked a long time, but
Yeah.
nothing came. So,
This
but
is ongoing.
It's ongoing.
I can't, yeah. So we're just happy to know because we just know that they have definitely a strong component like along the A-axis, along the atomic chains. But which
Would they
mode
be
is
the
this?
shear modes? Or?
We hope. That's also our point because again, that
Sure.
would be that they modulate the distance between the, yeah. So
We don't really know the frequency of the shear
no,
So far.
no.
so far.
If you tell me it's 4 terahertz, I'm happy. So, yeah, so that was actually what I like. So this is like apparently lattice unperturbed, so doesn't affect it by the photoexcitation or not that we switch any phase. So let's concentrate on the dynamics of the electronic structure. And this is done by photoemission. So in the first place, I'm showing you the dynamics of the occupied bands, which, for example, already at the gamma point show like a shifting behavior of both the upper valence bands, which occurs like at excitation times, and then it recovers on a few picosecond time scales. Now, we want to follow this shifting dynamics of the bands to see whether we can somehow decouple effects with you, connected to the screening. I mean, so free carriers, something like in the frame of like photoexcited semiconductors from a potential signature of exciton condensates. So let's see whether we can do this. And for that, I first show you the dynamics of these two parts of the occupied band structure, so the lower valence band at gamma and the dispersive part of the upper valence bands, where we expect already from equilibrium studies that the excitonic coupling should not be that relevant. What happens is that the upper valence band at large momenta undergo like a upward shift behavior, and the amplitude of this shift increases with the increase of the excitation density and saturates above the critical excitation Fc. The lower valence band at gamma has a very comparable behavior, I would say, which again connects this upward shift dynamics to the number of free carriers excited at the gamma point. Now, we check that this upward shift of the valence band corresponds like to a conduction match which does not shift in the same direction, which is already an indication that like it's not just like a rigid shift, but indeed that the conduction band moves oppositely and thereby that the band splitting is reduced at this momentum. And to do this is what you were asking before, so we perform this kind of experiment, so photo-exciting electrons into the conduction band and photo-emitting them with a second probe photon photon pulse.
In this case, which is the pump energy used?
It's still 1.55. So it's the same as before, so 800 nanometers. So this is just basically would pump like from just below the valence band into the conduction band. Yeah. So basically, this is the first excitation, and then we have a controlled delay between the two pulses. But this photon energy, the second pulse, cannot photo-emit from the occupied state, because it's just lower than the work function of the system. So basically, our signal comes only from unoccupied states. Is that? So you're not convinced?
Yes, in principle convinced, in practice not.
Why?
Because the work function of this material is X, and then
Yeah.
the eventual, if there is any excitonic band gap, will be of the order of 0.1 to 0.2 eV.
Mm-hmm.
I don't think you have that resolution to distinguish electrons being emitted from the top of the valence band or the bottom of the conduction band. Then I think you couldn't excite from there.
So the work function of this material is 5.4.
This I didn't.
The probe photon energy is like 5.3, 28, which means that we cannot really probe below the, like from the valence band with this photon energy. And I can show you, this is the data, and what you see here, for example, which is the very lowest intensity, or this big peak, is already inelastically scattered electrons, so which have no relationship with any bands, and it's just background.
My point is the following, maybe I'm completely naive. You have to do a transition with 1.5, which is way below the bottom of the conduction band.
Okay.
Then this has to relax.
Mm-hmm.
And in all those processes with the next photoelectron, you can excite it from both the top of the valence band or the bottom of the conduction.
The top of the valence band you will never be able to photoemit, because
if
you
there
would.
is no excitonic insulator, you do.
You cannot photoemit because they will stay below the vacuum level. So the problem is that basically, so this is your vacuum level, and like the photon energy can maximum peak from here, and there is no states.
But
So-
you have created carriers with the pump.
Yeah, exactly. So that's why you need two photon photoemission process to bring electrons at least like here from, let's say, the lowest, some lower valence band, and then you can pump outside the vacuum level. So without the first excitation, the conduction band is not only emptied, but like you cannot do it with one photon of the probe pulse. So this is actually, of course, you can have like two photons with the same pulse, but this would be like a sort of like non-time resolved signature, which you can get like this. It's a static spectrum.
So just you know, sort of from independent measurements, let's say in a simple picture, the number of electrons taken out of the valence band and put into the conduction band.
Yes.
And you know the amount by which the gap narrows.
Mm-hmm.
So therefore, from the ratio of those two things, you get Takeshi's V, which is the excitonic insulator interaction energy, right? I mean, there should be almost a direct one-to-one relation within some theory, because the whole point of the V is that it's this.
But are you referring to reduction of the band with temperature?
No, with excitation. You said that with photoexcitation, you know how many electrons you take from the valence band into the conduction band, and you know how much the band narrows.
So we, actually, we're at this large momenta, so not at the bottom.
Okay, but
Okay.
if you have a guess at the bottom,
Okay.
but surely that is almost enough to pin down completely the parameters of the interacting theory and to make.
I'm not sure because I'm not sure because if we first of all we of course always look at a finite energy momentum window. So there are other transitions which we are not looking at. So also saying exactly how many electrons we are putting in, and we don't look at all the electrons excited. And also this interaction, I believe, being also sort of momentum dependent, and to really get a quantity of the V, I would expect we would need to look more towards the bottom of the bands, isn't it?
Right. It's true that the interpretation would be more clear if you had a complete extrapolation to the bottom of the band.
Yeah.
But I still think this is very compelling information.
We could, yeah. So we didn't try to separate this information. So for now, was already I mean, of course, as soon as we saw this shifting behavior, first of all, we wanted to see whether there was some just pure shifting potential or other mechanisms, and it was quite interesting for us to see that we have like a redshift of the conduction band at this momentum, and also that this redshift is fluence dependent, so we can connect the upward shift dynamics of the valence band with the downshift of the conduction band. And
to be on the numbers, how big is the redshift and the blue shift?
So we are speaking about a few tenths of milli-eV in the upper in the valence band. In the conduction band, it's actually lower. So relatively here we are like at higher fluencies, but this can be also connected to overall like different character of the bands. But overall, like the behavior is consistent with a reduction of the band splitting. So the point is, like, of course, here we are not proving any modulation of the fundamental band gap because we are of gamma. So let's look actually what is happening at the flat valence band top. And what we find is that if we stay at modest excitation, let's say below this critical fluence FC, the system behaves like basically comparable to the rest of the occupied bands. And so we have again like an upward shift of the valence band top, which increases if we increase the pump fluence. So far we would say the system behaves like nothing but a photoexcited semiconductor. Now, if we crank up the power above this critical excitation density, actually a much more complex dynamics of the valence band top is observed only at the gamma point. So we have this upward shift of the valence band already almost instantaneously, and then followed by a delayed downshift of the valence band that brings the valence band transiently to a higher binding energy than the equilibrium position, which means that at this time scale we observe like a increase or widening of the electronic band gap at the gamma point. And this widening persists up to approximately 1 picosecond, and then is sort of overshooted by a very slow upward shift dynamics, which again reduce the band gap on a several picosecond time scales. Now, this early widening of the band gap is clearly opposite to the behavior expected for a semiconductor. So our attempt was to interpret this as a sort of dynamical fingerprint of an excitonic condensate, and also due to the fact that this dynamics is observed only in this sort of special part of the band structure, the flat valence band top. Let's see, to convince you about this, so let's first sum up. So we see overall a renormalization of the band structure in analogous to what happens for a photostatic semiconductor, and this dynamics appears to be connected to excitation of free carriers at the gamma point. And this is signified by this saturation of the upward shift dynamics of the valence bands, which occurs once we undergo like a pump absorption saturation at gamma.
Yes.
How does this?
Yeah.
If you link this to Eduardo's widening that you also see,
yeah.
So what is happening with the width of these bands?
So I must admit we never actually looked so much in detail about the broadening. Yeah, the bands also broaden, of course. I would say, so if I remember correctly, the broadening follows the dynamics of the shift, although it might be actually a bit slower dynamics. So the recovery of of the width at equilibrium, of course, on a longer time scale.
What is happening to your top of the band, and what is happening to a potential fill-in of the band when you start shifting spectral rate into the gap? So if you integrate the spectral rate in the gap, is this also less, or you still shift more into the gap?
So you're asking whether basically, apart from this shift, you would sort of like fill the gap by some further spectral weight due to the broadening. Yeah, the broadening is quite substantial, and I would say enough for filling the gap. But on the other hand, what we are picking up here is the peak-to-peak distance.
Yeah,
so in that sense,
this is where you have the peaks of the bands.
Yeah.
Can I make a general comment for the ultra-fast community, which is the following? So we should be able to find a good way to set our time zero in our traces. Mm-hmm. In the sense that it's very important to understand what the dynamics is of the system. And then looking at different papers, time zero is put in different ways, you know? So for example, looking at, the interpretation of the band gap renormalization, you say that it's immediate within the pulse, which is something that, in the 1980s, people were reporting in semiconductors, in semiconductor physics, they were pumping, and then because of the, change in the exchange and correlation potential, people were seeing band gap renormalization. So, but in that case, the time zero was set at the beginning of the trace. So here, if you look at your traces, there's a rise time.
Okay.
Because your temporal resolution will be 100 femtoseconds, I guess.
Yeah.
So there's always a rise time involved. So I totally believe the data. It says that they are crystal clear, but the interpretation of the band gap renormalization doesn't convince me, just because in the real data there's a rise time of the response, which is 500 femtoseconds or so on, or 100 at least.
Sure, but
so that's the only. So we should find a good way to set time zero for all of us, not just you or me or everybody.
But you will agree that this dynamics is rather abrupt and
So for example, time zero for me it should be.
And the question is do you really need this So first of all, it's rather abrupt, and also if you deconvolve it from this is not deconvolved with a temporal resolution, right?
That's right.
And rather than speculating on how much instantaneous is that,
That's
also
right.
because how much instantaneous becomes depends also on how much you're exciting, because the screening buildup that would be responsible for these dynamics is depending on excitation density, and also each material might have a response which differs. I would say the indication that this effect is fluence dependent points towards an effect which is related to free carrying non-screening.
I suggest we can
exactly
continue this discussion all night, because it would be nice if you could conclude it.
Yeah, exactly. So actually my point is we have this other dynamics, this widening, and so I told you at the beginning we have these two mechanisms. One is at the gamma point, and which is saturating it above this FC, and one is at larger momenta. We cannot probe at that momentum but optical data told us that it's most likely not saturating. So, and this is the transition that I'm sketching here. Interestingly, this transition at large momenta is creating a non-equilibrium population across the upper valence band and the lower valence band, which are supposed to be excitonically coupled. So our idea was, why shouldn't be that this mechanism is a dominating one, and particularly it's responsible for an increase of the condensate densities upon photoexcitation, which allow us to transiently enhance the order parameter connected to the excitonic phase. And to see whether this is of any relevance and whether it's meaningful, we collaborated with Dennis and Philip Werner, which performed a calculation of a out of equilibrium band structure for a very simple model, a two-band semiconductor where an interaction Coulomb term is added to account for a opening of a gap already at equilibrium, such that the expectation value of excitons is non-zero. And what they did was to introduce only two ingredients which could reproduce the experiments. So on the one hand, they reduced the non-interacting splitting of the splitting of the non-interacting system, and this should mimic our band gap renormalization observed in the experiments at early times. And the second thing is to consider a non-equilibrium carrier population, so a population which has not relaxed across the band gap, and then recalculate the band structure for an interactive Hamiltonian. And what they found is that at large momenta, indeed, the band splitting is reduced, and at the gamma point, the two bands are moved apart, and a widening can be observed. And not only this, they tested that this effect of band gap widening relies, yes, on the interaction between the two bands, but also on the presence of a non-equilibrium carrier population. And to do this, they put the same amount of energy now in a high temperature Fermi-Dirac distribution, and clearly the effect disappears. And nice agreement is also again with the data, which shows at later times that indeed thermalization of the system kills this widening and leads to a quasi-thermal reduction of the band gap. So we believe that in the comparison with the experiment and this relatively simple model allows us to extract two simple ingredients that on the one hand can explain the widening of the band gap, and the two ingredients are like a band gap renormalization, which somehow like can bring the two bands closer to each other and make them more interacting, and the presence of a non-thermalized population which prevents the temperature of the condensate exceeding the melting point. And so at the same time, so this is consistent with believing that such a widening like is sort of connected to an excitonic coupling and can be therefore taken as sort of like a fingerprint that tantalum nickel selenide like might host like an excitonic insulating phase. So sum up, very quickly.
Here, why you think this is an evidence of an excitonic coupling?
So it's like the model tells us that in a sense, like if we want to reproduce the experimental observation, we have these two ingredients to consider. So
there are other systems that exhibit the same type of behavior, and they are not excitonic insulators.
So of band gap widening,
yes.
For example?
Gallium arsenide. You increase the PAM fluence and then first reduce and then increase.
Okay, I'm not aware of this.
Most semiconductors, they do that. They behave as a function of fluence. They first reduce and then they increase.
Well, maybe they have an excitonic component.
Maybe they have an excitonic, yeah, exactly.
Another option.
That would be the question. If you do the same experiment in the sulfide, would you see a similar dynamics?
That could be actually a good test. Yeah, I mean, we don't claim that we have deep final proof. We are saying like the two pictures are consistent and like. So we found that this would be like actually the simple model because we are like in a sense taking the minimal amount of ingredients in the band structure and the minimal amount of interaction we might consider, and they can reproduce all these the effects like the splitting reduction, the opening, and also even the long time scale dynamics.
I think we should let Selene conclude the talk because we are already way over time.
Yeah. So let's make it even more simple. And so free carrier excitation, I've shown you how can efficiently couple to the lattice like by coupling with like excitation at the gamma point. And there is this absorption saturation at gamma, which is sort of like the blocking mechanism for a photoinduced structural change. So the lattice doesn't change upon photoexcitation. We found that on the other hand, photoexcitation of free carriers definitely like impact on the screening, and this is signalized by the band gap renormalization observed in the system, but also the presence of interband interaction seems to be important for like for impacting on the order parameter, in the sense that we found a regime where we can observe a enhancement of the band gap that, I mean, in our explanation and according to the theoretical model, is connected to this like excitonic coupling between the valence band and the conduction band. And in a sense, this is a mechanism that prevents the system from sort of photoinducing a phase transition. And interestingly, like this is likely supported by the fact that like the monoclinic structural phase also doesn't change. And this can be sort of like a support, like a characteristic of the system to avoid the electronic phase transition to happen. And yeah, that's the picture we sort of try to put together. And yeah, thank you for your attention.
Okay, questions, discussions, lots of questions. Okay, so I think Danish raised his hand first, so go ahead. He was also involved in.
I actually have a question for Angel.
It's
nice that it would be covered here.
Well, then if it's a question for Angel.
He's out.
No, he's not out, but
I want the communication between them. So I would understand that here the most strange thing which is happening is that we have a momentum-dependent change of the gap. So at the gamma point, So at the gamma point, it's increased, but away from the gamma point, we have renormalization toward. Do we know any other example of this kind of a behavior? So that we have momentum-dependent change in the gap. Because, yes, do we know any other behavior like this? Because this is why we took it as an example of excitonic behavior, excitonic insulator behavior.
Okay. No, I don't want to. Okay, there
Yeah, sure.
Also with Ralph, since already 3 years, we are trying to understand what is the signature of an exciton in a photoelectron spectrum, in a time result photoelectron spectrum.
Yeah, okay.
Just to make the story short, we conclude that we don't know. There is no way to see it, and all those things of renormalization that we are discussing can be, in all cases, interpreted in terms of a simple single particle picture. That's the conclusion. Then I'm not answering your question, but I'm telling you that we miserably fail to have excitons in Lattice.
Single particle.
So maybe just a.
Multi-band.
In,
We have multi-band.
Yeah, no, this doesn't mean it's not possible. It means that we don't.
I say the momentum dependence can tell us that there is a different character of the carriers between large momenta where the bend is pressed and this flattening. And simplest explanation seems to be this, but yeah, sure, yeah. Maybe it's just to comment on the gallium arsenide dynamics that there is momentum independent, I believe.
Not really. It's momentum.
Also not really. Okay.
But it's not as striking as the one that you see.
Mm-hmm.
If you go one slide back, you had this dynamics of this first.
In the model?
Yeah. Yeah, the modeling where you really look at the dynamics of the valence band shift. First it shifts in, then you have the widening. So I can take now basically this half a picosecond, that would be now in your picture because you form now new excitons. Then they are not in the condensate yet, and that would be then the time scale that it takes that they condense with the existing condensate. So I could take this half a picosecond as the condensation time scale. Provided in this.
In the picture of you open the gap because you increase the condensate density, you could say, yeah, the maximum you reach it. Yeah, I mean, if you want, also the fact that the idea that you have to consider this kind of population to for accounting for the external condensate density to increase, and yeah, those external have to find the gamma point first, if the gamma point is the minimum.
Okay, Peter?
No, thank you. This is lovely. I'm not really sure if this is a question for you, but since I have to leave, I'll ask it now anyway, and Antoine can answer it. But look, I mean, if you sort of accept this model that everybody likes, which involves a kind of pairing actually in the chain, there are two ways to do this. You can pair up and you can pair down, right? So then, because the state will be ferroelectric at some level, there's dipoles, we've seen very large dielectric constants. So that leads you to think about polar versions of SSH, where it will be natural when you start making photoexcitations, you generate electron-hole pairs, they can end up in different places, and in particular they can bind to antiphase domain walls and produce extra structure associated with all of that. Now, I think it's sort of a requirement that those things should be present, right? So, but what would it look like in experiment? I mean, typically it would look like things appearing mid-gap at longer times, and I mean, long meaning maybe not that long actually. But I think the message you're saying, however, is that you don't see anything happening at all in the middle of the gap. There's, everything is at the band gaps, right? Mm-hmm. But I should be starting to produce localized sort of breaking of symmetries that would allow the system to create mid-gap states in some transient way. And that's all, I mean, look, that's what you see in, the polyacetylene type stuff and all of the things we were used to in 1D, in charged, in other kinds of charge density ways. So it's not here?
I must say that already experimentally it's really hard with photoemission to look inside the gap. I mean, for photoemission, this is a small band gap. And already looking at the bottom of the conduction band, not even underneath, quantifying this signature is really hard, if not dangerous. It's like, I would say, and then trying to extract any quasi-particle peak inside of the band gap, you have to disentangle this from a huge background, so I would not do it.
Oh, I see. So you say it might be there.
I mean,
but you think it would be too dangerous
what I believe that like the way the valence band and the conduction band broaden after photoexcitation is such that their tails might even overlap, and whether this can raise give to a rise of a quasi-particle peak in the band gap. Well, I don't believe it because we believe that we are effectively not destroying the gap. On the other hand, even if you can't really disentangle. I mean, I've shown you the 2pp data where we look at the conduction band. There is really a huge incoherent background that is, for technical reason, you can't remove it and you can't even reduce it. And I believe it would be really, I mean, I would not like to do it. I like to have safe data to speak about.
More questions? Giacomo?
So is it possible that this momentum differentiation comes from the, let's say, the fact that you don't have a perfect particular symmetry, namely that the valence band has a different bandwidth with respect to the conduction band, and then it has a different curvature,
so,
let's say. So.
Did they have a different bandwidth? It's clear. Maybe I can show you.
Different 50 mass.
Sorry? Yeah. So
basically different effects.
Yeah, I know what you mean. So, I mean, this is actually if you want. Yeah?
No, great.
Okay. So, the valence band, I mean, this is emission angle and this is in momentum, but we would already say like the dispersion of the valence band, I mean, the scale is not the same, so the dispersion of the valence band is higher than the dispersion of the conduction band. This is already no, wait a second. It's the opposite. So, but yeah, sorry, I should think of it. But yeah, so they do have different dispersion, and also this extremely pronounced flattening, at the gamma point. I mean, those are symmetrized data. And I mean, this flattening is pretty much pronounced for the valence band. I would say less for the conduction. So they have different characters. They are also coming from different ions, so it's not surprising.
It can be that if you have two asymmetric bands that you move closer each other, then the fact that they have the symmetry.
So what?
And due to the electron-electron interaction gives rise to this momentum differentiation without taking into account any excitonic mechanism, actually.
I should think more about this, but I think that it could tell us something about how fast this electron-hole pair can recombine, because of course, depending on how the tube, I mean, you need to have the two bands being sort of parallel to. Let me think. I need to think more about this. Like, what I can tell you is that definitely the dynamics of the whole population and the electron in the conduction band are really different in the time scale. So the conduction band is depleted much, much faster. Where the electrons go, who knows? Yeah, that's not good. But so in that sense, they definitely have different characters, and yeah, whether this can be enough to describe the momentum dependence of the gap, I'm still not sure though. So, because I mean, in their case, they use absolutely like symmetric bands, and that's actually was the mechanism giving the widening that we observe. So.
Okay, given that we're all hungry, I suggest we maybe stop the discussion and thank all the morning speakers again. Discussions.